Hi there, welcome to brilliantmaths.com, where every student has an opportunity to excel in maths. Subscribe to our website. You have lots and lots of resources to help you excel. Today's lesson is actually taken from Brilliant Maths Module 7. Get a copy and let's go to class. In this part of the lesson, we want to look at nets of solids, nets of solid objects. But what is a net? A net is a plane figure showing all the faces that form a solid shape or a solid object when folded. So it's actually a plane figure. What we have on the board here is the net of a cuboid. So take a look at it. A cuboid has 6 faces, like we all know, and these are the 6 faces. 1, 2, 3, 4, 5, 6. This is not a very regular net of a cuboid that most people are used to, but we can see that it can actually form a cuboid. So we have that as the base of the cuboid. We can actually use this to fold up the cuboid. And this becomes the top while the sides close up. You can see that it forms a cuboid, and that is the net. Here I have the net of a cuboid too. This is a more regular one, just like a matchbox. If you cut up a matchbox, this is the kind of net you would get. And from this net, it has some dimensions on it, and you can actually calculate the total surface area. So when you have the dimensions of any net, you'll be able to find the total surface area of that object. The next net we want to look at is the net of a cube. Again, I have a net that does not look like the net of a cube, but there are several nets of a cube, and cuboids too. The most important thing is that you can fold it up to make the shape. Before I continue, the 6 faces, 1, 2, 3, 4, 5, 6. And then how does it fold up? This covers it, and the one at this side covers that side. And we have our cube, as you can see. So this is the net of a cube. It's not the regular one that you're used to, but you just saw us fold it into a cube, so it's correct. So this is a net of a cylinder. As you can see, these are the top and bottom faces, and this is the face that goes round to form the cylinder. So that is the net of a cylinder, and we have folded it to form a cylinder. Next, let us look at this net. What does it look like? How many faces does it have? It has 1, 2, 3, 4, 5. But there's something peculiar about it. The side faces are triangles, but the base is a square. So in folding it out, you can see that this is a net of a square-based pyramid. Not a prism, but a pyramid, because it all ends at the tip. Square-based pyramid. So this is a net of a square-based pyramid. Next, want to look at one more net. What can you see? 1, 2, 3, 4, 5. Again, the base is a pentagon. So this is a net of a pentagonal pyramid. Remember that the pyramids and the prisms get their names from the shape of the base. So this is a pentagonal pyramid. The tips end with triangles, and then the base is a pentagon. For more on nets of solid objects, get a copy of Brilliant Maths Module 7. We are continuing our lesson on similarities. Today we are looking at similar or congruent shapes. When are two shapes said to be similar, and when are they said to be congruent? Two plane figures are congruent if one fits exactly on the other. They must be the same size and the same shape. The concept of congruency talks about absolute equality. For two shapes to be congruent, it means that they are the same shape, the angles are equal, and the sides of the shape are also equal. One must fit in the other without any difference. But it's different for similarities. Two polygons are said to be similar if they are equiangular. That means their angles are equal, and also the ratio of the corresponding sides are equal. For example, we have triangle ABC and triangle PQR, as you can see on the board. Angle A corresponds with angle P, and both of them are equal to 105 degrees. Angle B corresponds to angle Q, and they are both equal to 40 degrees. And angle C corresponds to angle R, and they are both equal to 35 degrees. Then, what do we mean by corresponding sides? AB corresponds to PQ. BC corresponds to QR, and AC corresponds to PR. So we are saying that AB over PQ is equal to BC over QR, and that is also equal to AC over PR. In writing out the ratio of the corresponding sides, maintain a pattern. Whichever triangle you start out with the sides on top, maintain it across. If you start with the sides of triangle ABC on top and triangle PQR at the bottom, maintain it. If you decide to start with the sides of triangle PQR on top and triangle ABC at the bottom, then maintain it. But that ratio is equal to K, and K is the constant of proportionality or the scale factor. Let us look at another example. In this example, we have two triangles, triangle DEF and triangle ABC. And we are supposed to find the length of the sides marked with letters. So some sides have been given, and we're supposed to find the ones that are unknown. So from the two triangles, triangle DEF and triangle ABC are said to be similar. That means that the angle at D, as we can see, corresponds with the angle at A. The angle at E corresponds with the angle at B, and the angle at C corresponds with the angle at F. Can you see that? So, ratio of corresponding sides. DE corresponds with AB. So, DE over AB will be equal to DF over AC, because DF also corresponds with AC. And we're finding the unknown sides C and A. So let's put in the dimensions. DE is equal to 5, or 5 centimeters, and AB is unknown. AB is C, lowercase c. DF is equal to 4 centimeters, and AC is equal to 2 centimeters. We have a complete ratio here, 4 over 2. That can actually tell us that our scale factor of enlargement is actually equal to 2, because 4 over 2 is equal to 2. We can work directly with this, but just hold that. So having 5 over c is equal to 4 over 2, we cross multiply, so that we have that 4c is equal to 10. And if 4c is equal to 10, that means c is equal to 10 over 4, which is equal to 2.5. So that means that length AB is equal to 2.5. So 5 over 2.5 will also give you 2. One is half the other. That means that triangle DEF is double triangle ABC, as we can see, because DF is 4 centimeters and AC is 2 centimeters. So we have found the length of C. So to find the second length, which is the length of A, we know that DF over AC is 4 over 2. That is the complete ratio that we have. And then EF is 6 centimeters over BC. We don't know the length of BC. But since we know that the scale factor is equal to 2, we can simply divide 6 by 2 to get the length of A. So 6 divided by 2 is 3. A will be equal to 3. But trying to work out these ratios, then we have that 4A is equal to 12. So A will be equal to 12 divided by 4, which is equal to 3, which is the same answer. So try to identify the corresponding angles and the corresponding sides of any two given similar shapes. Let's look at one more example. In this third example, we want to find the value of x. We have two triangles. We have a small triangle ABD inside triangle ACD. And the two triangles are similar. We want to find the length of x, which is the length of DE. How do we do that? So let's look at the corresponding sides. AB corresponds to AC, and BD corresponds to CE, and AD corresponds to AE. So we have that AB over AC, the ratio of the corresponding sides are equal. So AB over AC is equal to BD over CE, BD over CE, and that's also equal to AD over AE. So let's see the dimensions that we are given. We need to find x, so we are finding DE. So we need this set of ratios. We need the AD and the AE, and we were given BD and CE. So we're going to focus on those. BD is equal to 45 over CE is equal to 60. And that is equal to AD is 39 over AE. AE is 39 plus x. We want to find the value of x. So you cross multiply and you have 45 into 39 plus x is equal to 60 times 39. So take out your calculators. 45 times 39, 45 times 39 is equal to 1,755. So 1,755 plus 45 times x is 45x is equal to 60 times 39. 60 times 39, and that will give us 2,340. 2,340. So that means that 45x is equal to 2,340 minus 1,755. And what would that give us? It will give us 585. So 45x is equal to 585. So what's the value of x? We divide 585 by 45, and that gives us 13. Therefore, x is equal to 13 centimeters. So you could be asked to find the length of AE. Then what will you do? You'd add the value of x to the value of AD. Similar triangles are very easy. Questions relating to similarities are very easy to solve, and you can get lots of practice from Brilliant Maths Module 7. So we have found that the length of x is equal to 13. We actually forgot to talk about the scale factor of enlargement. The scale factor of enlargement is our k. That is 45 over 60. The ratios that were given, 45 over 60. What is 45 divided by 60? 45 over 60 is equal to 3/4. That means that the small triangle is 3/4 of the bigger one. The small triangle is 3/4 of the bigger one. So to check, let's see if our answer is correct. Because if 45 over 60 is equal to 3/4, then 39 over the length of AE should also be equal to 3/4. So what is the length of AE? X is 13. So AE is AD plus DE. 39 plus 13 will be equal to 52. So K, or the scale factor, should be equal to 3/4. So let's see if 39 over 52 would give us 3/4. 39 divided by 52. Try it out. What did you get? I have 3/4. So the answer is correct. Our scale factor is 3/4. The small triangle is 3/4 of the bigger one. In this lesson, we are looking at the area of similar shapes. We want to be able to find the area of similar shapes using the fact that we know that the shapes are similar and we know the ratio of their corresponding sides. But we should note that if two figures are similar and the ratio of the corresponding sides is k, which is k is the scale factor, then the ratio of their areas is k squared. That's k raised to the power 2. So for example, we have triangles AXY and triangle ABC. AXY is the smaller triangle and it's inside ABC, but they are similar. So where are the corresponding sides? That means that AX corresponds to AB and XY is parallel to BC like we are given. In the diagram, XY is parallel to BC. If the area of triangle AXY, which is a small triangle, is 4 centimeters squared. Find the area of triangle ABC. So we have the area of the smaller triangle, and we're supposed to find the area of the big triangle, using the fact that the ratio of the corresponding sides are equal. So we know our K. So solution, triangles ABC, ABC, and AXY are similar. Ratio of corresponding sides, I am doing big over small. The bigger triangle over the smaller triangle. So the sides of ABC over the sides of AXY. So we have AB is 3 and AX is 2. So we know those two sides, so we can find our K. We can find our scale factor. So it's 3 over 2. That means that the big triangle is 1.5 times the smaller one. Interesting. So the ratio of their areas is 3 over 2 squared, because 3 over 2 is our K. That's the ratio of the corresponding sides. So the ratio of the corresponding areas will be K squared, which is 9 over 4. So that means that the area of triangle ABC over the area of triangle AXY is equal to K squared. So that area is equal to 9 over 4. But we want to find the area of triangle ABC. So we cross multiply. We have that ABC is equal to K squared times the area of AXY. And we were given that the area of AXY is 4 centimeters squared. So we have 9 over 4, which is our K squared, times 4 centimeters squared. The 4's will cancel out, and we have 9 centimeters. So that means that the area of triangle ABC is 9 centimeters squared. In this example, we want to find the length of X, knowing the area of the two triangles that are similar. So let's go. Example, two similar triangles have areas 18 centimeters squared and 32 centimeters squared, respectively. If the base of the smaller triangle is 6 centimeters, find the base of the larger triangle. So we know the area of both triangles, and we want to use that information to find the length of the unknown side. So solution, we know that the ratio of corresponding sides is equal to K, but the ratio of corresponding areas is equal to K squared. That is the scale factor. So here, ratio of areas is K squared. We know the areas. The area of the small triangle is 18 centimeters squared, and the area of the large triangle is 32 centimeters squared. So I'd like to use the area of the bigger triangle over the area of the smaller one to find our K. So K squared is equal to 32 centimeters squared over 18 centimeters squared, and that gives us 16 over 9. So the ratio of corresponding sides is K. How do we find K? Then we find the square root of that. So K is equal to square root of K squared, which will be the square root of 16 over 9, and that gives us 4 over 3. So the ratio of the corresponding sides is 4 over 3. We have the big triangle over the small triangle. So we know the length of this side, which is 6 centimeters for the smaller triangle, but we want to find the length of X. So the length of X over 6 will be equal to K, which is the ratio of the corresponding sides will be equal to 4/3. So x is equal to 6 times 4/3. 3 there, 1. 3 there is 2. And 2 times 4 is 8 centimeters. So since this length is 6 centimeters, x is equal to 8 centimeters. We have used the information on the area of the two similar triangles to be able to find the length of an unknown side. You can get more examples from Brilliant Maths Module 7. Next, we want to look at the area of similar shapes, but this time we're looking at a circle. A circle of radius 14 centimeters has an area of 616 centimeters squared. What is the area of a circle with a radius of 7 centimeters? So from this question, we can see that the radius of the big circle is 14 centimeters, and the radius of the smaller circle is 7 centimeters. The area of the big circle is 616 centimeters squared. We want to find the area of the smaller circle. How do we do that? From the information we have two linear measures, the radius of the small circle and the radius of the big circle. So that will give us our k, our scale factor. So radius of small circle is 7, and then the radius of the big circle is 14. So that means our k is half, putting the small circle over the big circle. So the small circle is half of the big circle. Then remember that for the areas, the ratio of corresponding areas is equal to k squared. So if our k is equal to half, then our k squared is equal to half squared, which is 1/4. So next, the area of the small circle over the area of the big circle is equal to k squared. Remember, we said we should be consistent. If we're putting the small circle on top, then let's do that consistently. If we're putting the big circle on top, then we'll do that consistently. You should get the same answer if you do it properly. So that should give us our k squared. We know the area of the big circle. So to find the area of the small circle, what do? We simply cross multiply. So therefore, area of small circle equals area of big circle times k squared. And our area of big circle is 616 centimeters squared times k squared. And our k squared is 1/4 times 1/4. What would that be? That means that the area of the small circle is 1/4 of the area of the big circle. So 4 into 61, what would that give us? 4 into 6 is 1. Remember, 2 into 21 is 5. Into 16 is 4 centimeter squared. So this is very interesting. The radius is half, but the area is 1/4. It will be good to use other smaller dimensions to actually find it out. That is where we know that the radius of the small circle is 7 centimeters and the radius of the big circle is 14. So let's say that the radius of the big circle is double the radius of the small circle. So if we're putting the big circle on top, our k is 2. So that means that our radius has been doubled from small to big. So the relationship between the linear measures is times 2. But the relationship between the areas will be times 4. Because if the radius of the small circle is 7 centimeters and the area of the small circle is 154 centimeters squared, then you double the radius of the small circle to get 14 centimeters, What happens to the area of the big circle? It is 154 centimeters times 4, which is 2 squared. That is where we have our k as 2 and our k squared as 2 squared, which is 4. So the area of the big circle is actually 4 times the area of the smaller circle. I hope you enjoyed today's lesson. It was actually on similarities. I mean, we learned how to find the ratio of corresponding sides. We looked at congruent triangles. We looked at the area of similar shapes. Get a copy of Module 7 of Brilliant Maths and you'll get lots and lots of resources, examples and exercises to help you. Subscribe to brilliantmaths.com. You are sure to begin to do well. And follow us on all our social media handles. And always remember that maths is fun and you can do it. My name is Ngozi Orebodine. See you again soon.